Welcome to today's deep dive, where we are looking at something you probably never think twice about. I mean, usually when you need a computer cable, you just fish some tangled mess out of a desk drawer, right?
Right, yeah. For most of us, a monitor cord is just a total commodity. It's cheap, you plug it in, and you completely forget about it.
Exactly. Maybe it costs you 10 bucks online. But our mission today is to figure out what happens when you take that disposable piece of plastic and wire and engineer it for, mission-critical applications.
And that completely changes the game.
It really does. We have a spec sheet today for what looks like an ordinary cable, but it's the DVIGear DVI-2315-SHRD dual-link DVI-D cable. It is 15 meters long, and it costs $340.
No, that is definitely not your average desk drawer cable.
Not at all. Okay, let's unpack this. How exactly does a basic computer accessory transform into this high-stakes piece of engineering to justify that kind of price tag?
Well, it really all comes down to the sheer physics of transmitting high-frequency data. Because when you send massive video signals over long distances, you're constantly battling these three main enemies, which are signal loss, skew, and jitter.
Right. And you can't just fight that with standard wiring, I assume.
No, absolutely not. To combat that, this DVIGear cable uses a 26-conductor setup packed with really heavy-duty 22 AWG copper wiring. What's fascinating here is how these specific physical traits guarantee what the specs call unsurpassed digital fidelity.
Let's clarify that wire thing for a second for everyone, because AWG, American Wire Gauge, is actually a bit counterintuitive. Like, the lower the number, the thicker the wire.
Exactly, yeah. Your standard cheap desk cable might be, 28 or 30 AWG, which is basically angel hair pasta, but 22 AWG is incredibly thick copper.
Oh, wow. Okay.
And that matters because it gives you lower electrical resistance. Take skew, for example. You are sending parallel streams of data down multiple wires. If one wire slows the signal down, the signals don't reach the monitor at the exact same microsecond, and the image just tears or drops out completely.
And jitter is when the timing of those data packets gets erratic.
Spot on. So that thick copper is crucial.
But it isn't just the thickness of the copper that stood out to me. It's how heavily protected it is. I mean, you've got this triple shielding wrapped around the wires, terminating in 30 micro-inch gold-plated connectors.
It's seriously heavily armed.
It's like a VIP motorcade for your data. It acts like a literal Faraday cage, serving as an electromagnetic sponge to absorb stray radio waves and electrical noise from the outside world.
Keeping that delicate data signal completely pristine.
Right. But I have to admit, I am a little confused by one detail in the specs. It says this cable has an operating temperature range from -13 to 140 degrees Fahrenheit. Do you really need extreme temperature resistance just to plug in a screen?
Well, it definitely sounds like overkill if you're just picturing like a nice air-conditioned office.
Yeah.
But you have to consider how heat actually impacts copper.
Okay, how so?
This cable is pushing massive PC resolutions, up to 3840 by 2400 at 60 hertz. That results in a staggering data rate of 4.95 gigabits per second. As ambient temperatures rise, the electrical resistance of the copper increases too.
Ah, so higher resistance degrades that high-speed signal.
Precisely. If this cable gets too hot, the data essentially chokes.
So the environment is actively fighting the data transmission. That is wild.
It is. And distance only multiplies that resistance. Even with heavy-duty 22 AWG copper and triple shielding, physics has its limits. At 15 meters, this specific cable is already pushing boundaries.
Right, really? Just 15 meters.
Yeah. The specs explicitly note that if you want to stretch beyond 20 meters, which is about 65 feet, you have to use an active cable extender. That's a power device that catches the fading signal, cleans it up, and re-amplifies it.
And even with that active boost, I saw the heavy-duty copper maxes out completely at 60 meters.
Exactly. There's only so much you can do with copper.
Well, here's where it gets really interesting, and I think it connects perfectly to your point about ambient heat. The spec sheet proudly lists dual UL ratings, UL13, CL2, and UL758.
Oh, right, the safety ratings.
Yeah, those aren't just random manufacturing codes. They are rigorous fire safety and toxicity standards. Achieving them means this heavy, high-speed cable is in-wall rated. It is designed to be permanently sealed inside building architecture.
That completely recontextualizes the temperature rating, doesn't it?
It totally does.
Because when you snake a cable behind drywall or, string it near industrial heating ducts or run it through the freezing outer walls of a building, you are exposing it to wild environmental swings.
And once it's behind a wall, it is incredibly expensive and disruptive to rip it out. It has to work perfectly the very first time, forever.
Exactly.
So what does this all mean for you, the listener? I mean, if you're designing a medical imaging lab, running a military control room, or directing a massive live stadium event, a dropped video feed isn't just annoying, it's catastrophic.
Yeah, failure isn't an option.
Right. This spec sheet reveals the invisible, ultra-reliable infrastructure required to keep those high-stakes environments running perfectly.
If we connect this to the bigger picture, it really highlights the vital role of physical, hardwired reliability. I mean, we live in an increasingly wireless world, but when a system is truly mission-critical, engineers don't trust the airwaves. They trust a heavily armored, triple-shielded pipeline of copper.
Which leaves us with a pretty fascinating question to ponder. We just learned that even the thickest, most heavily shielded 22 AWG copper paired with active extenders hits a hard physics limit at 60 meters. So what entirely different technology must engineers turn to when mission-critical video needs to travel miles instead of feet?